In this lesson, we will examine how predictions from the theoretically calculated electronic energies and orbital angular momenta of hydrogenic systems compare with experimental observations. When a high-voltage electrical discharge is passed through a sample of hydrogen gas at low pressure, light is produced. If the light is passed through a prism, a few lines in the visible region are observed. These spectral lines are part of what is called the Balmer series. The spectral line with the longest wavelength occurs at around 656 nanometers. Spectral lines of hydrogen are also observed in the ultraviolet and infrared regions. The experimental line positions are neatly summarized by the Rydberg equation. In this equation, nu tilde is the wave number, which you will recall is just the reciprocal of the wavelength lambda. R sub h is a constant, experimentally found to be 109,678 reciprocal centimeters. The N1 and N2 in the equation are integers. The spectral lines from 91 to 121 nanometers in the ultraviolet region are known as the Lyman series. For these spectral lines, N1 is equal to 1 and N2 are integers larger than N1. The spectral lines from 364 to 656 nanometers are known as the Balmer series. For these, N1 is equal to 2 and N2 are integers larger than N1. These include lines in the ultraviolet region, as well as the visible lines mentioned earlier. The spectral lines from 820 to 1875 nanometers are known as the Paschen series. For these lines, N1 is equal to 3 and N2 are integers larger than N1. Let's calculate the photon energies from the experimental line positions as given by the Rydberg equation. The photon energy is Planck's constant h times the frequency nu. The frequency nu of an electromagnetic wave is equal to c times nu tilde, where c is the speed of light and nu tilde is the wave number. Substituting the expression for nu tilde from the Rydberg equation and performing a couple of simple algebraic manipulations, we can show that the energy of the photon is equal to negative hc times r sub h over n2 squared minus negative hc times r sub h over n1 squared. Remember that n1 and n2 are positive integers, that n2 is larger than n1, and that the experimental value of r sub h is 109,678 reciprocal centimeters. Now let's look at the quantum prediction. The Bohr frequency condition says that the energy of any photon emitted must be equal to a difference between two allowed energy levels. What if we want to calculate the photon energy for the transition from a state with principal quantum number n2 to a state with principal quantum number n1? The photon energy would be equal to the energy when n is equal to n2 minus the energy when n is equal to n1. We can see that if hc times r sub h is equal to r, then negative hc times r sub h over n2 squared is the energy if the principal quantum number is equal to n2, and negative hc times r sub h over n1 squared is the energy if the principal quantum number is equal to n1. This suggests that the constant r that we obtained from solving the Schrödinger equation should be equal to hc times the experimental r sub h. If we calculate r from the experimental value of r sub h, we find r to be equal to 13.6 electron volts to 3 significant digits. We can see that there is perfect agreement with the theoretical value. Let's take a closer look at the quantum explanation for the Balmer series. The Balmer series of lines can be successfully explained as emission from excited hydrogen atoms. In a hydrogen lamp, the electrical discharge causes dissociation of diatomic hydrogen molecules to neutral hydrogen atoms. Any excited H atom formed can lose energy by emitting a photon. If one ends up in a quantum state with quantum number n equal to 2, then the photon energy corresponds to a spectral line in the Balmer series. In other words, the photon energies for the spectral lines in the Balmer series is given by E sub n minus E sub 2, where n is greater than 2. The photon energy calculated for the transition from n equals 3 to n equals 2 accurately predicts the spectral line position with the longest wavelength. The transition from n equals 4 to n equals 2 accurately predicts the next spectral line, and so on. Examine the allowed energies for the bound states of a neutral hydrogen atom as shown in this diagram. Note that, as a consequence of E being equal to negative RZ squared over N squared, as N approaches infinity, the allowed energy approaches zero, and the gap between adjacent energy levels also approaches zero. For the Balmer series transitions, which terminate on states with N equals 2, as N approaches infinity, the energy of the photon approaches are over 4, or 3.40 electron volts, and we expect the gaps between adjacent spectral lines to get smaller as N gets bigger. We can calculate the frequency and wavelength corresponding to this limit by using the equation that relates photon energy to frequency nu and wavelength lambda. It should be easy to show. To 3 significant digits, the lines for the Balmer series converge at a frequency of 0.823 petahertz, which corresponds to a wavelength of 364 nanometers. The SI prefix peta means 10 to the power 15. Here's a diagram showing the spectral lines of hydrogen versus wavelength in the ultraviolet and visible range. Here's the Balmer series. The so-called Balmer alpha line, corresponding to the lowest photon energy and longest wavelength, is the transition from N equals 3 to N equals 2, which occurs at around 656 nanometers. Here's the next line in the series. This corresponds to the transition from N equals 4 to N equals 2. Note that only the first few lines in the Balmer series are in the visible range of the electromagnetic spectrum. The rest are in the ultraviolet, with the lines converging at around 364 nanometers. This limit corresponds to the transition from N equals infinity to N equals 2. What about the other spectral lines shown here? Note that these are at even shorter wavelengths, further out into the ultraviolet range. The photon energies are higher. These spectral lines are called the Lyman series. These are transitions to N equals 1. The so-called Lyman alpha line, at around 121 nanometers, corresponds to the transition from N equals 2 to N equals 1. The convergence limit for the Lyman series occurs at around 91 nanometers. This limit corresponds to the transition from N equals infinity to N equals 1. Recall that the Bohr frequency condition requires that the photon energy must match the energy difference between allowed energy levels of a particle that absorbs or emits the photon. But just because the Bohr frequency condition is satisfied doesn't mean that an optical transition can occur. We can determine the probability of an optical transition from the wave functions. The probability can be shown to be proportional to the square of this transition dipole moment integral. The integral is evaluated by applying the dipole moment operator, typically represented by mu hat, on the wave function for the lower energy state, multiplying the result by the complex conjugate of the wave function for the upper energy state, then integrating over all space. If the transition dipole moment integral is 0, then the transition is said to be forbidden. Otherwise, it is allowed. For hydrogenic systems, the transition dipole moment is non-zero if the quantum number L changes by 1, and the quantum number M doesn't change by more than 1. In other words, for allowed transitions, absolute value of delta L must be equal to 1, and absolute value of delta M must be equal to 0 or 1. These expressions are known as the selection rules. A Grotrian diagram gives us a visual summary of the allowed transitions for an atom. The arrows connect pairs of quantum states for which optical transitions are allowed. A Grotrian diagram is an energy level diagram where each quantum state is represented by horizontal lines, as shown in the example here. This example graphically summarizes the selection rule that absolute value of delta L equals 1 for optical transitions in hydrogen. Note that there are no arrows between s orbitals. The change in quantum number L for a transition between any pair of s orbitals is 0. Transitions between any pair of s orbitals is forbidden. For example, the transition from a 2s orbital to a 1s orbital is forbidden. Likewise, there are no arrows between any pair of p orbitals or any pair of d orbitals. We also do not see any arrows between a pair of s and d orbitals. Remember that quantum number L is equal to 0 for s orbitals and 2 for d orbitals. So, the change in quantum number L for s to d, or d to s, transitions is plus 2 or minus 2. Therefore, these transitions are forbidden. If we carefully examine the arrows shown in the diagram, they represent transitions between s and p orbitals, like this one between the 2p orbital and the 1s orbital, between p and d orbitals, and between d and f orbitals. These transitions correspond to a change of 1 in the quantum number L. Here's an example illustrating the selection rules for optical transitions in hydrogenic systems. Which of these two transitions is allowed? A. 2pz to 3p plus 1. Or B. 4p0 to 3dxy. Let's examine choice A. For the 2pz, quantum number L is 1, and quantum number m is 0. For the 3p plus 1, quantum number L is also 1, and quantum number m is plus 1. So, there's no change in quantum number L, which makes this transition forbidden. Even though the change in quantum number m is 1, which is allowed, the transition is forbidden. Both selection rules must be satisfied. How about choice B? For the 4p0, L equals 1 and m equals 0. For the 3dxy, L equals 2 and the absolute value of m is 2. Recall that the dxy spherical harmonic is a linear combination of spherical harmonics with m equal to plus 2 and minus 2. Here, we can see that the change in L is 1, which is allowed. But the change in m is 2, which is forbidden. Therefore, the transition is forbidden. Neither one of these transitions is allowed. The correct answer is D. Let's now talk about ionization energy. Ionization refers to the removal of an electron from an atom. For hydrogenic systems, this can happen if an electron gains enough energy from photon to excite the electron from a bound state to a free or continuum state. The ionization energy, IE, is defined as the minimum energy needed to remove the electron. In other words, for hydrogenic systems, it is just the energy needed to excite the electron to the quantum state where n equals infinity. Since the energy is 0 when n equals infinity, it's easy to see that the ionization energy is just the absolute value of the bound state energy. Consider a hydrogen atom in the ground state. The principal quantum number, n, is 1. The energy is minus 13.6 electron volts. So, if we want to remove an electron from this atom, we can do so by hitting it with a photon that has at least 13.6 electron volts of energy. What would happen if we use an even higher energy photon? For example, what if we use a photon with 15 electron volts? In this case, the extra energy becomes kinetic energy of the free electron. 15 minus 13.6 equals 1.4. So, the free electron will have a kinetic energy of 1.4 electron volts. The idea here is basically the same as in the photoelectric effect. Ionization energy is analogous to the work function. From which of these orbitals would it be hardest to remove an electron? The 1s orbital of a hydrogen atom, the 1s orbital of a hydrogenic helium ion, or the 2s orbital of a hydrogenic helium ion? To answer this question, we compare the ionization energies. The electron will be harder to remove from an orbital that corresponds to a higher ionization energy. For choice A, Z equals 1. There is one proton in the hydrogen nucleus. For the 1s orbital, the principal quantum number n is 1. The ionization energy is the absolute value of the orbital energy. The 1s orbital energy is negative R. So the ionization energy is R. For choice B, Z equals 2. There are 2 protons in the helium nucleus. For the 1s orbital, the principal quantum number n is 1. The ionization energy is 4 times R. Doing a similar calculation for choice C, we find that the ionization energy for an electron in the 2s orbital of a hydrogenic helium ion is R. So, The correct answer is B. Note that you should be able to figure this out without doing any calculations. Let's compare choices A and B. In both cases, the electron is in a 1s orbital, but there are more protons in helium nucleus. So, it would be harder to remove the electron in choice B. Let's compare choices B and C. In both cases, the electron is in a helium ion. We compare 1s versus 2s. The energy in the 1s orbital is lower, and it would take more energy to remove this electron from the ion. We will now examine the angular momentum of the electron and its physical consequences. We will refer to the angular momentum due to the motion of an electron around the nucleus as its orbital angular momentum. Later, we will deal with another type of angular momentum called spin, which does not have an analog in classical mechanics. Recall that the functions associated with hydrogenic orbitals are written as a function of r times a spherical harmonic, which is a function of theta and phi. Since the angular momentum operators depend only on angles theta and phi, we can show that the wave functions are also eigenfunctions of the angular momentum operators. Here's how. If we apply the L-squared operator on psi, we can factor out the radial function since, as far as the L-squared operator is concerned, the radial function, which depends only on r, is a constant. In our lesson on the particle on a sphere, we learned that the spherical harmonics are eigenfunctions of the L-squared operator, with eigenvalues given by L times L plus 1 times h bar squared. After a few algebraic manipulations, we can show that applying the L-squared operator on psi gives us back psi times the same eigenvalue as the spherical harmonic. In other words, the magnitude of the orbital angular momentum of the electron in a given orbital is well defined. It is quantized and depends on quantum number L, just like a particle on a sphere. Similarly, it should be easy to show that psi is also an eigenfunction of the Lz operator, and the z component of the angular momentum is also quantized, with eigenvalues equal to m h bar, just like a particle on a sphere. We can determine the angular momentum of a charged particle based on how it's affected by the presence of an external magnet. This is because a charged particle with a non-zero angular momentum generates a magnetic field, which then interacts with the external magnet. Watch this video from Khan Academy for a quick review of the basic ideas linking movement of electrons in a loop to magnetism. You can scan the QR code to watch the video on your mobile device. For a particle with charge q, mass m, and angular momentum vector L, the magnetic dipole moment vector is obtained by multiplying vector L by a scalar equal to q over 2m. So this means that an electron in an orbital with quantum numbers L and m will behave like a magnet, and we can get the magnitude of the magnetic dipole moment by multiplying the magnitude of angular momentum by E over 2 times m sub E, where the m sub E is the mass of the electron. Here, E is the magnitude of the charge of an electron, which is 1.602 times 10 to the negative 19 coulombs. The charge of an electron is negative E, but we use the absolute value if we just want the magnitude. The mass of the electron, m sub E, is 9.109 times 10 to the negative 31 kilograms. We find the magnitude to be square root of L times L plus 1 times mu sub B, where the constant mu sub B is called the Bohr magneton. The Bohr magneton is equal to E times h bar divided by 2 times m sub E. Its value is 9.274 times 10 to the negative 24 joule per Tesla. As for the z component, we multiply the value of L sub z, which is m times h bar, by negative E over 2 times m sub E. The z component is equal to negative m times mu sub B. Note that the m here is the quantum number, not the mass of the particle. We can see that mu sub z and L sub z have opposite algebraic signs. This is because the charge of an electron is negative. In other words, the magnetic dipole moment vector for an electron points in the direction opposite to that of its angular momentum vector. The direction of the magnetic dipole moment vector is what we could think of as the south pole to north pole direction of a bar magnet. Let's look at an example. What is the magnetic dipole moment due to the motion of an electron around the nucleus if it's in an s orbital? Pause the video to think about it, then resume to check your answer. The magnitude of the magnetic dipole moment is equal to the square root of L times L plus 1 times the Bohr magneton. Since L is 0 for an s orbital, the magnetic dipole moment is 0. This means the motion of an electron around the nucleus does not generate a magnetic field if it is in the s orbital. Let's look at another example. How would you describe the magnetic dipole moment due to the motion of an electron around the nucleus if it's in a 3D plus 1? First, we need to figure out the quantum numbers L and M. Okay, for a d orbital, quantum number L is 2. The quantum number M is specified in the question as plus 1. The magnitude of the dipole moment vector is square root of L times L plus 1 times the Bohr magneton. Since L is 2, the magnitude is square root of 6 times mu sub b. The z component of the dipole moment vector is negative of m times the Bohr magneton, or negative mu sub b. Let's sketch this vector. Here's the xy plane. Here's the z-axis. Here's the vector. It is pointing downward since the z component is negative 1 times mu sub b. Square root of 6 is about 2.45. So the length of the vector is about 2.5 times longer than its drop. We can calculate the angle that the arrow forms with the negative z-axis to be about 65.9 degrees. Don't forget that there is uncertainty in x and y components of the vector. So we say that the vector is precessing about a cone of uncertainty at a fixed angle of about 65.9 degrees from the negative z-axis. The tip of the vector can be anywhere on this circle that is parallel to the xy plane. What if the electron is in the 3D xz orbital? Let's see. The quantum number L equals 2 since the electron is in a d orbital. So the magnitude of the magnetic dipole moment is square root of 6 times the Bohr magneton. The z component is negative of m times the Bohr magneton. But the quantum number m is not well defined for the 3D xz orbital. Recall that the spherical harmonic for 3D xz is a linear combination of 3D plus 1 and 3D minus 1, with coefficients of the same absolute value. Therefore, there is a 50% chance that m is plus 1 and a 50% chance that it is minus 1. How many ways can a magnetism generated by the orbital motion of an electron in a 3p orbital be oriented with respect to the z-axis? Is it 1, 3, 5, or 7? Let's see. Since quantum number L for a p orbital is 1, the quantum number m can be plus 1, 0, or negative 1. There are 3 possible values of quantum number m for a p orbital. The 3 possible z components of the magnetic dipole moment vector are 1 Bohr magneton, 0, and negative 1 Bohr magneton. The correct answer is B. The magnetism due to the orbital motion of an electron in a p orbital can be oriented 3 possible ways. We can say that there are 3 possible angles between the z-axis and the orbital angular momentum vector. Since the dipole moment vector points in the opposite direction as the orbital angular momentum vector, these are also the 3 possible angles between the z-axis and the dipole moment vector. The Zeeman effect refers to the splitting of atomic spectral lines in the presence of an external magnetic field. It serves as evidence for the quantization of angular momentum. It also provides validation of the selection rules for optical transitions. For example, in the presence of an external magnetic field, the Lyman alpha line at around 121 nanometers splits into 3 lines. The stronger the external magnetic field, the larger the separation of the lines. In the next slide, we explain why this is the case. How do we explain the splitting of spectral lines in the presence of an external magnetic field. Let's assign the direction of the external magnetic field vector as the positive z direction. The net effect of the external magnetic field is to change the potential energy by an amount equal to the dot product of the magnetic dipole moment vector of the electron and the external magnetic field B. Since we're taking the external magnetic field to be pointing in the positive z direction, the dot product is just the product of the z component of the magnetic dipole moment, mu sub z, and the magnitude of the external magnetic field. Recall that the z component of the magnetic dipole moment is just the negative of quantum number m times the Bohr magneton, mu sub b. Therefore, the allowed energies in the presence of an external magnetic field is obtained by adding m times mu sub b times b to the energy when there is no external magnetic field. We can see that the energy is lowered when quantum number m is negative and is raised when quantum number m is positive. But why? Think of the external magnetic field as a bar magnet with the south to north pole direction pointing in the positive z direction. If quantum number m is positive, then we think of the magnetism due to orbital motion of the electron as a bar magnet with the south to north pole pointing somewhat downward. When the north poles of two bar magnets are pointing in the opposite direction, that would be a less stable situation due to repulsion. We associate greater repulsion with a higher potential energy. Conversely, if the quantum number m is negative, then we can imagine the two bar magnets as attracting each other, leading to a lower potential energy. Note that if quantum number m is 0, there is no effect on the potential energy. Let's take a look at the effect of an external magnetic field on the Lyman alpha line of hydrogen. The transition from 2p to 1s corresponds to the Lyman alpha line at around 121 nanometers. For s orbitals, quantum number m is 0, and the orbital motion of the electron does not lead to a magnetic dipole moment. An energy of an electron in the 1s orbital will not be affected. But in the 2p subshell, the energy of an electron would now depend on which orbital it's in. For m equals 0, the z component of the magnetic dipole moment is 0, and the energy is not affected by an external magnetic field. Therefore, the energy of an electron in the 2p0 orbital will not be affected. But an electron in the 2p plus 1 orbital will have a higher energy by an amount equal to mu sub b times b. And an electron in the 2p minus 1 orbital will have a lower energy by an amount equal to mu sub b times b. We say that the presence of an external magnetic field lifts the degeneracy of the three orbitals in the 2p subshell. Let's visualize this with an energy level diagram. Let's say that this is the energy level for the 1s orbital, with or without the external magnetic field. All three of the 2p orbitals will be at a higher energy level. Let's say this is the 2p energy level without the magnetic field. The presence of an external magnetic field would lower the energy of the 2p minus 1 and raise the energy of the 2p plus 1. Instead of the same photon energy for all the 2p to 1s transitions, there are now three possible photon energies. The transition from 2p minus 1 to 1s will now lead to the emission of a lower energy photon at a wavelength longer than 121 nanometers. The transition from 2p plus 1 to 1s will now lead to the emission of a higher energy photon at a wavelength shorter than 121 nanometers. The transition from the 2p0 to 1s will not be affected. Thus, in the presence of an external magnetic field, we see three spectral lines instead of just one. Consider the Balmer alpha line at around 656 nanometers. These are due to transitions from 3p to 2s, 3s to 2p, and 3d to 2p. Into how many spectral lines do the 3d to 2p transitions split in the presence of an external magnetic field? Pause the video to figure out the answer. First of all, remember that quantum number L is equal to 1 for a p orbital, so the 2p energy levels split into three levels. For a d orbital, L equals 2, so the 3d energy levels split into 5 levels. You need to consider the selection rules that quantum number m cannot change by more than 1. The correct answer is 3. In fact, you can show that for all the allowed transitions, the splitting is 3 because of the selection rule that quantum number m cannot change by more than 1. If you need help, scan the QR code shown here to see the explanation at the Hyperphysics website.